We have been talking about three different types of programmable logic devices. PROM, programmable read-only memory, where you generate all the minterms and combine them in OR gates to get the different functions. Fixed and array and programmable OR array. Then we thought of programmable logic array, where we had the AND gates are reduced, number of AND gates reduced, so that we generate not all minterms of given input variables, only generate a few product terms from which we can get the output functions. So it was a programmable AND and a programmable OR. Then we looked at the third possibility of a programmable array logic, PAL, wherein that flexibility of generating the small number of product terms was kept, but the ROM, the outputs, the OR gate array was fixed. That means each output had an OR gate in which only a few of the product terms are connected, pre-connected, and you cannot change those connections. That means it is a programmable AND and fixed OR array. If you can really do a good job of optimization, programmable logic array is good. But in terms of in view of the practical difficulties, it is not very popular. So programmable array logic, in which you need to only minimize the corner maps, and then use appropriate size of the programmable array logic with proper number of input gates, input functions to each of those OR gates. That became very popular, and that's what we saw in the last two lectures, these three devices and simple examples. But I asked you to do the example of binary to 7-segment decoder using ROM, PROM. You can also do it for PAL, programmable array logic array, programmable logic array. If you can do that, of course you need to specify the size of the programmable logic array. So depending on that, you will have to select the common terms. So if you know, only if you know what is the number of product terms available or given to you or you are allowed to use, then you can optimize it based on that. So but just make a general design with as few terms as possible, having as many common terms as possible. Do the same exercise, repeat the same exercise of binary to BCD to 7-segment display decoder using programmable logic arrays, assuming that we are allowed to, we are required to optimize or make as many common terms as possible between the different segments. Then come up with the size. You come up with the requirement. It may not be available in the market, that you may not have. You may have an odd number of number of AND gates and an odd number of outputs, but outputs are fixed, of course. 7 outputs, 4 inputs. With number of product terms, you minimize it, taking into account the common expressions. And then you can repeat the same example with the programmable array logic. There you will have to know, of course here again 4 inputs, 7 outputs, but you should know how many inputs are required to each of those outputs, each of those output OR gates. That I can't say now without minimizing it. So you individually minimize each of those segment logic A, B, C, D, E, F. Come up with a list of product terms and product terms for each one of them, and give us as a requirement rather than a fitting in a given design. You come up with a requirement. I can do this if you can give me 7 OR gates, one of them with so many inputs, one of them with so many inputs, like that. So give me a listing of how many inputs should each of those OR gates require. So that will complete the exercise of all the three. Of course, we did simple example in the class. I am asking you to do a slightly more extensive example with more inputs and more outputs and more number of terms, so that you have an idea of the design. You can call it homework. Do it. Okay. Now let us move on, and as I said, programmable array logic is a very popular device today in the design of ICs, in the design of digital systems using programmable devices, as against the design using gates or medium scale integrated circuits. There are varieties. There is a variety of devices available. Of course, one is the manufacturers. Two types of varieties are, one is the different manufacturers make them. That is only a product thing. Second variation is the type of device. How many inputs, how many outputs is okay, that we need for a system, but how many product terms can it generate, and what is the composition of the inputs of each of those OR gates. So you will have to give a specification. For example, PIL spec specification, give you number of inputs available, number of outputs, and then number of inputs to each OR gate. As an example, if I have a number of inputs 4, number of inputs outputs 5, I don't think that these are some arbitrary things. There are standard devices. Now, it is not enough if I say 4 and 5. I will have to say each of these 5 outputs, how many OR gates, how many product terms can be connected to the OR gate which lead to each of those outputs. So I will have to say, in addition, number of inputs to each OR gate. That means I will have to say, for example, 2, 3, 3, 2. That means I have 5 OR gates. First OR gate will have, so it is like this. Second one, so forth. 3, 3, 2. Total number of product terms will there be 2 plus 3 plus, this is what? 9 plus 4, right? 13. That means number of product sums is 13 in this case. There is no use giving this unless you know this structure. That is what I am saying. No use telling you that I have 4 inputs, 5 outputs and 13 product terms. You just minimize it. Use it to get an implementation. Next question you will ask me is, how are these 13 product terms connected to the different OR gates? If I don't tell you that, because there is no way you can change those connections. Whereas in a PLA, this is enough. This and this enough. So I can reuse them in different OR gates, right? So in a ROM, I need an input and output alone, number of input, number of outputs. In a PROM, in a programmable logic array PLA, I need to know inputs, outputs, and the number of product terms, because each of those product terms can be given as inputs to each of those OR gates. So I need not tell you how many of those product terms are connected to each of these OR gates. In the third variety, namely the programmable array logic, I need to tell you not only the number of inputs and number of outputs, to tell you how these product terms are distributed as inputs to the OR gates. Of course, the total number is not of consequence to us. You don't have to count the total. If you want, you can count it, but you don't have to. So that means in the selection of a device for your application, you go, first of all, you have to choose the manufacturer of choice for what reason, because of the price or reliability or the type of device that you are looking for is available with that manufacturer. I will not go into that as a commercial aspect. Then you have to look for this value. So that means there is a variety there in the product, the manufacturers, there is a variety in the type of devices. So these are standard. I am going to talk about another variety today, types of outputs. Because this PIL has become such a popular device, a lot of people are putting a lot of things and make it more and more attractive for people to use. So they are coming up with features which are useful to the designer. so that those devices will be chosen as against in preference to a competitor's device. That is the reason. Types of outputs. What do you mean by that? See, each of these product terms F1, F2, I mean functions F1, F2, etc. We normally, as I said, till now it is only combination logic. I have been saying combination logic design using programmable logic devices. Is that right? So we will have a output function in terms of P0, P1, P2, P3, etc. Now, simply like this, each of these is an AND gate. These are the inputs A, B, C, and their counterparts also. Supposing it's make it simple. Let us say we have A and B as inputs, A bar, B bar available. So all my product terms can be functions of A bar, B bar. Is that right? That's what I mean when I say two inputs. Now, and I am assuming that I have the first product term which combine this in some way. This is symbolic. I will put an AND there. I don't show all the inputs. I just show there's an AND gate which can take any of those inputs. You can take as many of these inputs as required and make a product term. So this is my P0, P1. This is how you find it in the data sheet. If you look at the data sheet of a programmable logic array, there will be a diagram, block diagram. You can see it in the books also, in the digital logic book, programmable logic devices chapter. If you look at, they will give you a symbolic description of some of the devices, commercially available devices. And how do they represent it? That they represent this will tell you that there are two inputs possible and four product terms possible. Each of these product terms can be functions of A bar, B bar. And then of course, there will be a third one which will tell you this. This is my F1. This is a pictorial or schematic representation of the PAL. Now, what do you mean by type of outputs? This is a combinational input, combinational output. Normally, we assume positive logic, positive logic. Normally, we assume we have a variable A and B, and then when they take certain values, output is true. Other cases, the output is false. So we assume that high is 1. We put high. 0 is low voltage, high is high voltage, right? 1 is high voltage, 0 is low voltage. That is the assumption, input and output. This is called, as I already told you, this is active high logic. A logic in which 0 is represented by lower of the two voltages. A logic has only two levels, 0 and 5, 0 and 3.3, 0 and 15 if you want it, if you want to really have it occasionally, 0 and 1.2 volts, whatever. Low voltage is 0, high voltage is 5. I mean, high voltage is 1. This active high logic. On the other hand, I may want a situation in which I want active low. That means I may have a NOR gate as the output. So first is active high output. So type of outputs. First is active high, second is active low. What do you mean by active low is, I can have a F1 and F2 as NOR outputs rather than OR outputs. The reason is, you know that De Morgan's theorem and all that we have seen it in simplification of logic. Sometimes it is attractive to give a solution in terms of the complement of the function, that is simpler function compared to the true function which is more involved. Or maybe the output of this needs to be lower in order to drive a device. I am going to drive this F1 and F2, I am going to use these outputs to drive devices which will work if the voltage is low and stop when the voltage is high. Possible? Yes or no? It's possible. It's a possibility. So in that case, I would like to synthesize circuits whose outputs are low rather than high for a given combination of inputs. So I want that combination, you have it. So you can, all you have to do is look for the device. That means you have to go through the data book in conventional terms or the modern terms, it is the web or the go to the website of the product manufacturer and give the requirement, and they will give you these are the devices, this type of output. So you will say, not only it's enough if you say I want 4 inputs, 5 outputs, I want this type of combinations of the outputs in AND gates, and also I should say active high or active low. Then there is a NOR. I mean NOR is already there. Exclusive OR outputs. I can have XOR output. What do you mean by XOR output is, I can have groups of normally this is what it is, and I can combine these two. So this is P1, P2, P3, P4, this is P1 or P2, P3 or P4, and this is P1, P2, exclusive OR, P3, P4. So if you want to synthesize a function in this form, it can be also single. I am just giving you, I can also put P1, P2 and exclusive OR them. That is what I would like to have in an adder. Suppose you want to implement an adder, full adder using this, or a parity checker, parity generator, code generator. Remember we did some of those things earlier. But it is not necessary that only one of those terms should be as in to the XOR. XOR will have 2 inputs, but each of those inputs need not be a single AND product. It can be a OR combination of several AND terms. Both are possible. Likewise, I can have an XNOR output. All I need to do is these are nothing. All you have to do is just change output, get to the requirement. What is the big deal? Of course, point is these are available. The idea is to go for as few ICs as possible. We don't want to do logic outside of this. If necessary, of course, you may have to do it. But you need a device, a chip in which you will do everything, program it for your application. In small applications, in mechanical applications, in non-electrical applications. When some signal is coming and they have to convert into electrical signal and do some processing and put it back as a mechanical signal. They don't want to have a huge electronics there, just a little device which will just begin. Many of these gadgets which appear very big but non-electrical gadgets, like a mixer at home or a washing machine, you will find that it will not work, but then the moment that service fellow comes and then replaces the chip, it works. Only one, nothing else. That's because in one chip they do everything there. So in such cases, don't say, okay, I only have active high, you need to put an inverter when you want to. So my device only takes active low for functioning, you are giving active high, so you say go to an inverter. You say inverter fine, I can give you, but then for that I need to get a voltage source. So many things are there, second socket, etc. That is the reason. Idea, as I told you, is to give flexibility for the designer with options which are normally found in electronic circuits. It's not big, it's not a big deal to do all this. But what is slightly different, is somewhat big deal, is we can have what is known as a programmable I/O. What is the programmable I/O? Supposing I want, in this case, 4 inputs, 5 outputs. It's a very small device, so you generally don't have a problem. In fact, you will have a problem finding a device with 4 inputs and 5 outputs. You will find a device with 8 inputs and 8 outputs. That is the smallest we can get, possibly. Go and buy it. On the other hand, suppose I want 12 inputs and 4 outputs. And this fellow says I have 8 inputs and 8 outputs. Totally 16. I want total 16. but I can't use it because you are 8 inputs, I need 12 outputs, 12 inputs. Then I have to go for a 16 input device, or because that 12 may not be available, and then 16 inputs may have 16 outputs or 8 outputs. Device size becomes much larger. See, I don't know if you are not walked into electronics lab so far. I don't know how many of you have walked into electronics lab. The same lab where you go to check your mail in the ground floor of ESB, the same lab is used as a digital lab next semester. But I don't think any of you showed curiosity to see what is the other things, what are the other things available in the lab. We just try to go to the computer, check your mail and come back, right? Browse the internet. All you need is a little curiosity. 2 minutes extra, and there are lots of people sitting there, or lab technicians, lab assistants and lab supervisors who can help you. They want somebody who is interested, because they have only a lab class in the afternoons, and they will be very happy to, for a student to, if a student goes to one of them and asks, I would like to see an IC, do you think they will be happy or not? They will be very, very happy. I'll show it to you. Why don't you try doing it when you go to the digital lab next time? Same lab, you need not go anywhere else. Same lab you go for your mail checking. Anyway, there, you look at the ICs, there are different sizes. Usually there are 20 pins. 8 inputs, 8 outputs, 16. Power supplies, ground, and some, maybe there's a clock requirement or something. There are some standard packages. These are called standard packages. I don't want to give the types. There are designated, there is type number for each of those packages. I may not know all of them, but even if I know, there's no point in reciting them here. 20 pin package, 16 pin package. But then there's nothing like a 22 pin package, nothing like a 24 pin package, there's nothing like a 30 pin package. So if you leave the bus, there may be 8 pin package is there, 8 is there, 16 is there, 20 may be there. Then if you leave the bus, you need to go for 40 pins. So my problem is becoming more and more complicated now. I wanted 8 inputs, 12 inputs, 4 outputs. I have only 8 and 8 with the 20 pin package. If I lose it, I have 16 pins input and 8 pins output, or even 16 and 16. 16 inputs, 16 outputs, and 40 pin package, and it's double the size, some lengthwise, because pins, it's a physical, mechanical. I may put a million gates in a small IC, small area, because we are talking of dimensions of nanometers today. Microns and submicrons is the dimension. But inside you can do anything, etching and all that, electron beam lithography, so that you can make a line which is as thick as thin as the size of an electron or molecule, molecular epitaxy, electron beam epitaxy, laser epitaxy and all that, laser etching and things like that. But then I put 1 million gate functions, and then I want to put it, seal it, you can give it to as a customer. It should have a mechanical ruggedness. I cannot. It cannot be brittle. It has to be put on a base, which will stay. And then I have to make connections, because when I have 1,000 gates, naturally there will be large number of inputs and large number of outputs. So I will have to provide for all those inputs and outputs. That means I need a base with different pins for inputs and outputs, and the size they cannot be micron dimensions. How do you physically connect it to another device or a computer? So I need to have a minimum size. So when the size becomes larger, all our original concepts of size saving, everything has to be rethought. So we want a chip in which I would trade off. I want 20 totally, 8 inputs, 8 outputs. You are having 12 inputs and 4 outputs. I want 12 inputs and 4 outputs, but you are having 8 inputs and 8 outputs. If I can trade off 4 of those outputs for inputs, that will be nice. I can do with the 20 pin IC and then be very happy about it. That is the concept of programmable I/O. So certain pins are designated as IOs. It can be used as input or output based on your requirement. It is very interesting concept, right? Whatever you want is available in electronics. That is the beauty of today's technology. It is not individual making, but the technology has grown over years. 50 years of semiconductor technology has given you all that you want, and much more than what you can use really. So what is the concept of this programmable I/O? So I said I want only 4 of the 8 outputs available, but I want those 4 outputs to be used as inputs. Is that what I said? Okay. So this is a pin which is normally an output pin. This is my device, PIL, in which an output is coming. And normally an output, but I want this to be chosen as an input because I already have 4 of those. This is the 5th one, I don't want this as an output, I want it as an input. So what I need to do is just put a simple buffer here, or an inverter, whatever it is you want. You talked about the tri-stating, remember? Enabling a gate and disabling a gate, we talked about it. There's a state called high impedance state. So I'm going to put an enable here. So I can physically disconnect this, electrically disconnect this, even physically present. I can electrically disconnect this from here because this is, when it disables this, when this is 0, output goes through as an output. When En is 1, when enable is 1, this is disabled, which means there is no connection between output and input electrically. That means as if this is a mechanical projection available to me which has no connection to the rest of the circuitry. All I need to do is to use as an input. This is the same pin because the one output pin, this output pin will be used as an input now. Why I am putting this is, when I have a input like A, supposing this is a ABC, and let us say this is D input, call this D. I need both D and D bar, is it not? In my logic, when I have an input D, a new variable, I need to have both versions of that. So my input is not complete unless I give you the complement also. I can combine them. I can't go for an inverter inside. Inside is all AND gates and OR gates, so the inverter along with that. So this is the programmable connection. If En is 0, this uses an output pin. En is 1, this uses an input pin, and where a new input can be connected, and its complement also is available for implementing your logic using that extra input. This concept is called programmable I/O. Of course, this PIL is only my artificial, but the PIL is really the whole thing. This is the rest of the circuitry. So because this will come from a combination of AND gates, and this will go as inputs for all that type of thing. So the total thing is a PIL. What we had originally, normally I would have had this output available to you. Now I am putting this extra logic here, which can keep it as an output if you want by making En is equal to 0. If you don't want this to be an output, I make En is 1 and this is disconnected. Actually this AND gate is not available output. This OR gate or whatever, this is an OR function, it's not available. So I take this and use it as an input with this one complement and all that, and then it will be also used in my synthesis. This is my programmable I/O. So you cannot have both, of course. Some of them have to be programmable. If you want to use a device of this choice, you have to choose one with that feature. And once you have 16, 8 and 8, I cannot have 16 inputs and 8 outputs. That's not possible. Total of 16. But then manufacturer's data sheet, they will mislead you because it's something like selling. See, everybody wants to sell their products, so they'll say 16 inputs and 8 outputs. You have to be watchful, you have to be careful in reading those data sheets. What they mean is up to 16, like this price reduction, 50% off. You go to the shop, you'll see a small thing up to 50%, and then you say, what, 5 rupees off. See, normally it would have been so much, and now it is. So, but you went there because there was a big 50% off, and then you saw up to. You didn't see that up to. Similarly, they will tell you 16 inputs, 8 outputs. Manufacturers, I'm not joking, it's true. You go to a data sheet of any standard manufacturer. For a particular device, you will say 16 inputs, 8 outputs. You go there, they will say up to 16 inputs, up to 8 outputs, but not at the same time. Right? Sales gimmicks. The academicians don't know all those. Okay, so we want bare facts. And the last output is called registered output. Registered output is, what is a combination logic used in a sequential circuit? As a driving logic, as a steering logic. And what does it steer? Input of the flip-flops, right? This is used as an input of the flip-flop which steer the circuit from state to state. So if I can also put that flip-flop as a part of a PAL, I can finish my sequence circuit design in one single chip. Suppose I have a single chip solution for the type of some of the problems we did earlier, sequence detector and all that. We had combination logic, we had flip-flops outside. Those flip-flop outside need not be put now because these are ICs, small ICs. This is one big IC or large scale IC or medium scale IC, and you want to have extra small scale ICs, so put together, and again those extra logic, putting them together, wiring, all that come about. Oh, if I can push those flip-flops also inside the PAL, that is called a registered output. What I mean is, you have these outputs. Give a simple example. Registered outputs. This is my output 1, O1. I want this to be my input of the flip-flop, and the flip-flop will be the state variable which will be fed back. Is it not? You visualize that standard sequence circuit block diagram. We have the steering inputs, steering logic, output of the steering logic is the next state information which goes in the flip-flops, which becomes a present state after one clock cycle. So that I can do within the chip itself. So if this is my D flip-flop as an example, this is my output function Q, and this has to be used as a steering input also for the next. See, state variables also used as inputs, is it not? Present state variables are the inputs to the next state. So I want the output of this also fed back for available as inputs. Remember that this variable is O1, which is available here as O1, but this is O1 bar. So when you invert it, you have to make sure this is O1 bar, this is O1, this is O1 bar. The whole thing is within the IC. This flip-flop is inside the PAL. Output of an OR gate output of a PAL, combinational output, whether it's an active low or active high, doesn't matter, drives the flip-flop to the next state. The next state information is fed back. All that is part of this. That means a single IC, programmable array logic IC, with sufficient number of registers, a sufficient number of flip-flops inside it. So when I choose my outputs, I need to choose a variety of combination of outputs. I want some of them combination outputs for direct outputs, some of them as registered outputs. This is called registered outputs. Some of them are registered outputs, number of register outputs I need is equal to the number of state variables I want to use in my design. Supposing I have a 16 or 8 is a good example. Suppose I have an IC called 16 or 8. Sixteen inputs, 8 outputs. What he means is up to 16 inputs, 8 outputs. Okay. So 8 of them are inputs. Another 8, 4 can be registered, 4 combinational. Because you have to go into details of how many OR gates for each, how many connections to each of these OR gates and all that. We will not get into this. So this is also possible. You can select an IC with 4 registers, 4 non-registers as outputs. Then 8 inputs can be combined. So up to 4 variables, state variables, you can have 16 states, isn't it? A sequential circuit with up to 16 states can be implemented using a single IC. If you want more, of course, there are 8 registers also available. I'll just give you an example. So most of the textbooks, there will be a 16 or 8 diagram, especially some of the recent books. Please look at the 16 or 8 block diagram given in a textbook. I don't know which textbook, I don't want to name any textbook here, but already talked about some of these standard textbooks. Most of them have this. Mano has it. So you look at a 16 or 8 diagram, it will become clear. Registered outputs, or you can look for 16 or 4 also, 4 registered outputs. Since it is 16 or 4, up to 16 outputs and 4 registered outputs, which means other 4 can be non-registered outputs. 16 or 4 if you want is enough. And then all other features. But then when you have this programmable feature or this feature, you need extra inputs. You need a clock signal, you need an enable signal. All of them also have to be given. So when I decide the number of pins required, number of inputs, number of outputs, this ground and power supply, is there a clock required, is an enable required, all those things also take accommodated. So clock comes from, so this has to be clock, remember. So clock is one of the signals. So I need to connect clock also. So my pin outs, I have to account for the clock signal. How do I feed the clock into the chip? Through an output pin, external pin. So an external pin has to take a clock. External pin, through external pin only I can decide my enable signal. And then I need inputs, then I will take outputs. That's how it is. So you have now the variety of this, so you can know almost any design up to what you have seen. Small designs with pure combinational or pure sequential like registers, or a combination of registers and combination of sequential and combinational and sequential, everything can be done. So PIL, as I said, is a versatile programmable family, and people have used it in large designs now. It's a very popular alternative, and you'll have to go to the website of any standard manufacturer like there used to be one monolithic memory, MMI, monolithic memories industries. Most of them do it, I think. Analog devices, National Semiconductor is a major. So I would like you to go to one of those websites, National Semiconductors, look at their PIL alternatives, or you go to the lab and ask for a data book. Our lab, the same lab I was referring to, has data books. You can go and ask for a data book of a programmable array logic and see for yourself the varieties available. Each of them will have a diagram, the block diagram. So I want to spend the next few minutes on summing up this concept of programmable device. Design using programmable devices is very popular today because of the flexibility of the design, and you can change the design, size, everything. But what we have seen in the class till now are very small devices. So ROM can be of any size, but larger size means larger memory, space and power, and we don't want to use them. As I said, a large ROM is inefficient for a design, because a large ROM means large number of inputs and all the minterms are generated, When all the minterms are generated, only few of them are used, it is inefficient hardware utilization. So leave that out. ROM based design, one is required, they do it, lookup table approach, but generally when the size is small, only they use ROM. That means that leaves two other alternatives, programmable logic array and programmable array logic. I told you programmable array logic is more popular. We usually consider 4 or 5 or 8 inputs, for example 16 or 8 as give you an example, 16 or 4 is another example. 16 or 4 will be 8 inputs, 4 registered outputs and 4 non-registered outputs. Okay. Now these are all right for many problems that we do in the class, and also many small systems like elevator control. You go to lift, the control is a logic circuit in which there may not be more than this number of inputs and outputs. Traffic light control. When we talk of bigger systems like microcomputers, microprocessors, other electronics, process, as I said, rocket launch, avionics, and even other areas, plants. Large number of inputs and large number of outputs, that means this PLDs becomes inadequate. So there are two major, this is the trend now, the PAL, programmable logic device based design is a trend, but there are two, size wise it is growing. There are two things, two options for larger designs. There are many options, but two are more popular. One is called CPLDs. The other is called FPGAs. CPLD stands for complex programmable logic device. Nothing complex about it. It's a large number of PLDs, small PLD, each is a PLD. 8 input, 8 output PLD, 8 input, 8 output, 4 registered is a PLD. I put several of them in one single chip and give it to you. It's a complex PLD. That means all you do is to do the interconnection properly. Functionally the thing is defined, you can program the interconnection structure. So combination of groups of PLDs, programming structure has to be designed. Interconnection to be programmed. So we do this. These are interconnected through a sort of a matrix. This is a switch matrix. Which one is connected, which one is left out, and all that. So programming the interconnect basically. These are all PLDs all over the place, and they interconnect them. The FPGA is almost similar again, the concept wise, but then it's slightly different in the way, in the sense, it comes with what is known as logic blocks, the array of gates, programmable field gate array, field programmable gate array. So gate arrays are units made up of gates. You know, in a gate you can design multiplexer. The gate you can design a flip-flop. With the gate you can design exclusive OR gate and all that type of thing. So we have small units of gate arrays which are called CLBs. Configurable logic block. So about 100 gates, they will make a unit. Like that there will be several, it is an array of those 100 gates each. Totally there may be 10,000 gates, 100,000 gates, 1 million gates, 2 million gates are available today. So 2 million gate structure is available, 1 million gates are available. Let us not worry about such big, 100,000 gates are available. It is not that 100,000 gates is given to you in a big sack. Use it the way you want. They put it in front of you and you don't know how to do it. They make life simpler for you by grouping these 100 million gates into smaller groups. Each may contain about 30-40 gates or 100 gates maximum. Such a group is called a configurable logic block. So this the total available number of gates, available is grouped into smaller groups. Each one will have a specific function, like a CLB will typically consist of a mux. What are the various small things used for a design? We want a multiplexer, we want a flip-flop, we want a lookup table. Lookup table means memory. Now, how can you put a lookup table? Means you put a value and then read it when you want it. That's called lookup table. That means the memory. A small amount of memory, a flip-flop, a multiplexer, and a few gates. So that you can make a small design out of this. And like that, several groups are there, and each of them have the same standard features. Each of them will have a single mux, maybe 4-to-1 mux or something like that, a single flip-flop, a lookup table of a small size of 8 words, 16 words, and then a few gates, exclusive OR gates and all that. So the logic has been broken, your whole system requirement. You come up with the requirement of the logic and has been broken down into these small things. So your job is to break your design into these smaller groups and then interconnect them efficiently. So you have to map logic onto LU2 on CLB and also interconnect them. That is the difference between these two. Here there are all the standard PLDs which are familiar with. They are available. There is a switch matrix. You program for switching them properly, connecting them properly. You program only the interconnects. Here I have to map my logic. I have to break my logic into efficient blocks which can be fitted to each of these CLBs. And then not only you have to efficiently map them, you have to interconnect them efficiently. Both types are available, there are manufacturers, there is a lot of debate about this approach better, this approach better. There are some companies which are specializing on this, it's called Altera. This company is specialized on Xilinx. Now they are each convinced that other fellow has a market, then they want to do both. So now we may have an Altera, both companies may be doing, these are the two well-known companies in this, Altera and Xilinx. But Xilinx was originally famous for this, well known for this, Altera well known for this, but then now I think they are also having the other line of products. But then the problem here is what? The problem is how am I going to program? How am I going to? It's going to be formidable. It's going to be overwhelming. I'm given 100,000 gates and a huge system like a control circuit of a 8086 Pentium microprocessor. I'm asked to I give you 100 million gates, 100,000 gates, and ask you to design a control circuit for a Pentium processor. Problem is known, hardware is given. How do I do this? I give you a flight path of a trajectory of a space vehicle, all the various parameters, and then give you map it on this IC. So there are standard software available. This will be done only by what are known as computer-aided tools, also called electronic. EDA stands for electronic design automation. You have to do the electronic design automatically, but more efficiently. So you need a domain knowledge. Don't think that it's a C programmer or a Java programmer cannot do this job. You need to do it because you need to know some of these things. So there is a CAD tool available. So this is for another day. I am just giving you these details so that you should not be ignorant. So what we have seen is a small minuscule, the beginning of a whole revolution or whole range of big area of programmable logic devices, in which several alternatives like that and very, very large sizes. It's a big industry, both hardware and software. Tools are available. People constantly work on improving capabilities of the tools to map it efficiently. And you can work on design or you can work on even tool development. See you next time.